Hi everyone, I am Chandrika and I am from Purdue University. I am excited to present our work titled Shadowed Realities: An Investigation of UI Attacks in WebXR, done in collaboration with American University of Sharjah and University of California, Irvine. Let's begin by discussing extended reality or XR. Extended reality or XR is a broad term for technologies that blend real and virtual worlds. It's quickly gaining adoption in industries like retail, manufacturing, healthcare, education, and entertainment. Major tech companies like Meta, Microsoft, and Apple have launched their own XR headsets and development frameworks. Each headset relies on its own development framework, for example, the Meta XR Core SDK for developing apps in MetaQuest, and the Mixed Reality Toolkit for developing apps in HoloLens. Now, given the differences across platforms, in recent years, web-based XR, referred to as WebXR, has become popular. WebXR is a development framework that provides a unified way to enable XR experience for the end users across different headsets. WebXR allows users to interact directly through the browser of the head-mounted displays, such as MetaQuest or HoloLens. Unlike standalone applications, no additional software installation is required. Users simply navigate to the WebXR page URL and tap on the AR/VR button on the screen to enter the 3D mode. Once in 3D mode, similar to standalone XR applications, users can use their controllers, gaze, and even hand tracking to interact with the virtual objects within the scene. The ability to share WebXR experience simply through a URL makes it much easier to reach a broader audience. Also, the WebXR API is supported by most browsers such as Google Chrome, Microsoft Edge, Safari, and even XR headset-based browsers like MetaQuest browser. To develop WebXR apps, several libraries and frameworks such as iframe-3JS, Babylon.js are now available that allow developers to implement XR experiences with just a few lines of HTML and JavaScript. Even little code changes are required to support for both AR and VR. While WebXR shares a lot of similarities with standard web, there are a few key differences. For instance, in standard web, iframes are HTML elements that separate third-party content like ads from main web page content. However, there are no iframe-like elements in WebXR. As a result, in WebXR there is no mechanism such as same origin policy in standard web that blocks scripts from accessing resources across different origins. Other UI properties such as overlapping objects, transparency, and synthetic input help enhance immersion in WebXR scenes. For example, overlapping objects can be used to create complex scene architectures. Transparency can be used to create visual effects such as motion, shadows, water waves, or glass-like reflections. Synthetic input is used to trigger dynamic interaction between virtual objects without users' explicit input. Now, the lack of iframe can be exploited by malicious actors, such as a malicious developer or advertiser or ad service provider in WebXR advertisement ecosystem. Particularly, security-sensitive UI properties such as overlapping objects, transparency, etc. can be manipulated to incorporate dark patterns, forcing users into performing unintended actions. Let's consider a target shooting game scenario. A malicious developer may hide an advertisement within an overlapping object of identical size and shape. User sees the target game object from outside and not the advertisement. However, when the user clicks on the object outside, the click is received by the hidden ad. Now let's discuss another example where the ad service provider is malicious. Here, the malicious competing ad service provider exploits transparency or block users' intended action with a target object such as advertisement from other ad service provider. Such exploitation can lead to loss of sensitive user data or the installation of malware on their systems. These manipulations may further result in financial losses or reputational harm for the affected stakeholders. Through our research, we aim to address two key research questions. First, how do different UI properties contribute to the dark pattern designs in WebXR ad ecosystem? And second, how do different deceptive design practices within WebXR impact the overall experience of users and their interaction with the app content? Let's begin by discussing our key contributions toward answering research question 1. Our literature review identified 9 prior UI-based attacks, including cursor checking, blind spot tracking, and denial of service attacks. We then developed a 4-category taxonomy based on the primary objectives of the malicious actors in the WebXR advertising ecosystem. Let me begin with the first category, click manipulation. As the name suggests, these attacks aim to generate revenue through deceptive ad clicks. Next, we have peripheral exploitation. In this category, attacks leverage blind spots to inflate ad impressions or clicks. The third category is functionality disruption. These attacks are designed to prevent users from completing their intended actions. And finally, we have UI-based privacy leakage. These attacks are used to extract sensitive user information. We also proposed 5 novel UI-based attacks in WebXR ad ecosystem. These are visual overlapping and sequential rendering under click manipulation category, malvertising under peripheral exploitation category, GUI switch attack under UI-based privacy leakage, and finally, DOS to overriding attack under functionality disruption category. Next, we will take a closer look at visual overlapping and malvertising attacks. To discuss the visual overlapping, let's again consider the target shooting game scenario. For this attack, we consider the developer to be malicious. Now, the malicious developer strategically places an advertisement behind an interactive bait object. The developer makes the bait object unclickable. This ensures whenever the user tries to interact with the bait object, click goes to the next entity intersected, which is here the advertisement. Finally, synthetic input is used on the bait object to keep the functionality intact. Now let's discuss the malvertising attack in the same target shooting game context. Here the advertiser is considered malicious. A malicious advertiser provides transparent or part transparent advertisement. The user still sees the object behind the transparent ad. However, when the user tries to click on the object, the click is received by the transparent ad. This click can redirect a web page in the auxiliary screen of the browser of the head-mounted display without the user's awareness, as the user is interacting with the 3D scene. In summary, to answer research question 1, we proposed 5 novel UI-based attacks in WebXR advertising ecosystem. We also introduced a 4-category taxonomy covering 14 attacks and identified 14 contributing security-sensitive UI properties. We now move to the second part of our contributions, where we address research question 2. This focuses on investigating the impact of the attack categories on the user experience and their interaction with WebXR app content. To understand the impact of the attack categories, we need to capture detailed event information and also identify intentional and unintentional events based on the UI-based attacks. We wanted to understand whether the impact of these attacks changes when users interact with apps that differ in context and interaction demands. To do so, we designed a between subjects user study with 2 factors, attack category and app, for comparing attack categories with each other and control group. We recruited 100 participants all over the age of 18 from our university using an IRB approved method. Participants were evenly divided into 5 groups, 4 representing the attack categories from our taxonomy and 1 control group. Each group of 20 participants was further split into 4 subgroups based on app type. We selected reading, gaming, shopping, and travel apps. These apps were different based on the context and interaction demand. Each participant interacted with only one condition. We selected a specific app type and attack category and asked them to engage with 3 attack scenarios from that category. Or the same scenario was repeated in case of the control group. During the interaction, we collected 3D interaction data, and after each scenario, participants completed an online Qualtrics survey about their experience. We then analyzed both the interaction logs and survey responses to assess the impact of these attacks on user perception. To conduct the user study, we developed a user study framework consists of logging framework, interaction metrics, and a suite of applications. The logging framework is used to capture detailed event information and also identifying intentional and unintentional interaction with the main scene objects and the advertisements. We developed the logging framework with a single entry point and it consists of 4 components. We developed the framework using iframe and 3JS. Let's now discuss the 4 components of the logging framework. First, the environment scanner component monitors objects added to the scene to attach corresponding logger. Next, the T-object and DP-object logger captures 3D spatial data related to click, focus initiation, removal events, and based on the attacks also identifies intentional and unintentional events. Then, the cursor event logger captures simultaneous interactions by single cursor. And finally, camera and gaze logger estimates users' position and attention. We developed 4 interaction metrics to extract meaningful quantitative insights from the collected logs. First, presence metric helps us understand the user's focus on the given task. Second, the safe engagement metric helps us understand impact on user interaction with task under attack conditions. Since most of the attacks rely on unintended clicks, we introduced malicious attention metric to measure this effect. However, within the peripheral exploitation category, some attacks only work by rendering advertisements outside the user's field of view to inflate ad impressions and does not depend on unintended clicks. To measure the success of these attacks, we introduce the metric blind spot rendering fraction. Integrating 14 attacks in 4 apps, reading, gaming, shopping, and travel, along with 4 control group apps, and incorporating the logging framework in each of the app, we developed the application suite used in the user study. Let's now look at the findings from our user study, which we conducted with 100 participants. Finding 1 suggests that most of the attack categories go unnoticed by users. Particularly, other than functionality disruption, we found that the experience of users when attacks from other attack categories were integrated was similar to that of the control group. Next, we find that the presence is influenced by the app types and not attack categories. From safe engagement metric, we also find that the attacks force users to shift their engagement with a given task. We found that UI attacks are effective in achieving their objectives as seen by the malicious attention level that represents unintended clicks by the user. Blind spot rendering fraction also shows a significant difference between peripheral exploitation and the control group. These attacks happened consistently across apps with varying level of presence, suggesting generalization to different applications. As seen, WebXR is easily available, deployable, and can be used across different headsets. Beneficial UI properties enhance immersiveness of WebXR, but those can also be exploited to integrate dark patterns. In this study, we proposed 5 such UI-based attacks, developed a 4-category taxonomy identifying contributing UI properties, conducted a 2-factor between subjects user study to investigate the impact of these attack categories on user experience. To do so, we developed a user study framework that includes a logging framework, interaction metrics, and a set of apps, all of which we have made publicly available. The user study shows the effectiveness of the attacks. The developers and platform owners can use the list of identified properties and attacks to secure user interactions in WebXR. Thank you all for your time and attention. You can access the paper using the QR code, and please feel free to reach out to me via the email address provided.